Welcome, everyone. It's a real pleasure for me to present Fernando Cordero. He's going to be our speaker today. He's going to talk about speciation induced by dominancy in a model with changing environment. He's a Chilean working in Vienna, so for us it's a real pleasure to have him. All yours, Fernando.
Thanks, Hector, and thanks everyone for being here. Yeah, so it's indeed a big pleasure for me to show a bit of my research. From my formation, I'm a probabilist, but with the time I move a bit into the more applied side in population genetics. And what I'm going to talk today is a joint project with Adrián González Casanova from University of Arizona and Jason Schweinsberg from University of California, San Diego. And it is about something that is called speciation. And it is related to something we call dormancy. And there will be a third concept with which I will start, and is adaptation. So maybe we start with that, and just to for you to know, the more or less half of the presentation are known things, are not my results, and towards the end, I will talk about the project. But I think since many of these things are maybe new for some of you, I prefer to start a bit slow. So what is adaptation, or what are we going to understand as adaptation is the process of change by which an organism or a species becomes better suited to its environment. And the way we will see this here is with a very simple model. It's probably one of the simplest model in population genetics is the Wright-Fisher model, or a variant of it. And this is a population model of constant size. This means the population will consist of n individuals all the time and will evolve in discrete time. So time here are generations. We will go from time 0 to 1 to 2 and so on. And the idea is that, well, there are many things going on, and maybe the first one and the most important one for adaptation is that individuals will accumulate mutations. And mutations in this first model will be always beneficial. This means that whenever an individual gets a mutation, the individual will become more adapted to the environment. And we will call the type of an individual to the number of mutations the individual carries. So an individual that has get 3 mutations will have type 3, and an individual that have get no mutation will have type 0. And the fact that individuals will become better with more mutations will be reflected on the fitness of the individual, which will be 1 plus a constant, a positive constant, to the power k, where k is the type. So at the beginning, at generation 0, where we have not seen any mutation, all the individuals will have fitness 1. So that's the beginning. And now how the system evolves is as follows. So imagine we have constructed the population until time n, until generation n. So how we construct the new generation. So the idea is that each individual in generation n plus 1 will choose a parent from the previous generation uniformly at random. Every individual will choose his parent randomly according to the fitness. So individuals with higher fitness will have more chances to get picked as a parent. And then we decide on the type. So with a probability 1 minus mu n will be a number between 0 and 1. The type of the parent will be inherit, and with probability mu n, we will get a new mutation. So we either keep the type of the parent, or we get the type of the parent plus 1. So to convey and to show you a bit how this works, I have here a picture. So here, this is the time will evolve from left to right. And these white balls are my individuals, and they are all white because I want to convey the idea that they all have fitness 1. They are all equal. And now these lines connecting individuals from, do you see my mouse? Yeah, so the individuals here are generation 0, and then the individuals here will be generation 1, and the lines connecting them are depicting the ancestral relation. So this individual will be the parent of this one and of this one, and this individual will be the parent of this one. Yeah, and this is at the beginning when everyone has the same fitness. This is really uniform at random. And this will happen for some time. And at some point, we will see a mutation. Here is this light blue individual. He got a mutation, so he will be better adapted to the environment. He has more chances to be picked in the next generation. And then here, two things may happen. Either by pure chance, this individual may get washed out from the population, or it will start its way to fixation. So this is what happened now here in this realization. So this individual starts putting offspring in the next generations, and at some point it fixates in the population. And then we wait a bit more time, and then there may be a new mutation appearing that once more can get washed out or can go to fixation. And in this way, the population will get better and better adapted to the environment. So this is probably one of the simplest model of adaptation. And let us now
Fernando,
explain
just
a
to
bit.
see if I understood, the amount of individuals always keeps being the same.
Exactly. The population is constant. Exactly. So it's always n individuals.
Perfect.
And we are going now to see what happens when n is large. So here we have the parameters. N is the size of the population. Sn was this selection parameter, and mu n was the probability of a mutation. And then the quantities that we usually look at are, for example, for a given type J, to say what is the number of individuals with type J at generation n, or this quantity m star, which is the type of the individual with a higher fitness at generation n. That's also something of interest. And then what is called the speed of adaptation, and which is this infinite sum. Well, at any time it will be only a finite number of positive terms. And we have the proportion, the number of individuals with type J weighted with J. So typically, if things are as we saw in the picture before, most of the time we will see in the right time scale, we will see only one type of individual. So this means this quantity here will be typical. So in this sum, there will be usually only one thing that will be dominating. So if type K is dominating the population, I will get basically that mn is equal to 2k times the proportion. Well, the proportion of individuals at 1 will be 1, so it will be k. So mn will be k if there is one dominant type, and this dominant type is k. So there are, of course, the behavior of these quantities will depend on the parameters. And here I will concentrate on one parameter regime where things are very simple. So the first assumption is that Sn, selection, is constant, and people usually call this strong selection. So that's the first assumption. And the second assumption relates to the mutation probability. So the factor n mu n, so mu n was the probability of seeing one mutation, that one individual mutates. And since we have n mu n is the probability that we see a mutation in a given generation. And the logarithm of n appears here because when you see a mutation, this mutation conditional on survival will take order of logarithms of n generations to get fixate. So this condition here is telling me that mutations are rare enough so that we see one mutation at a time. Yeah, so we don't see many mutations on the way of one mutation to fixation. So one mutation comes, fixates, and then comes the next one. So that's a typical picture. And what happened for large time n, if we speed up time by 1 over n mu n, well, a constant time that, but more or less, what we see is something like this. So most of the time we will have type 0 individuals, and then after some exponential time, there will be type 1 that will appear and will fixate. And then after some exponential time, it will be type 3 that will appear, and so on. So you see something that takes this shape, and in expectation, you have something, this average fitness that I defined in the previous picture is something that grows linearly. So that is adaptation, and this Wright-Fisher model that we saw at the beginning is going to be the type of model we consider in the rest of the talk. But the rest of the talk is not about adaptation, it's about something different, and this something different is speciation. So what is speciation? So speciation is the formation of new and distinct species in the course of evolution. So I think this goes a bit, I don't know who introduced this term, but I think the full story starts with Darwin in a sense, no? So when he went to the Galapagos, well, in this big trip on the Beagle, and he realized on the Galapagos that there were in different islands birds that, well, looked very similar, but at the same time very different. And then he was wondering why this was the case. And then a bit later, he discovered that they were all members, or they were all members of the same species in a sense. So what happened to these birds? What they became so different in time? Well, this is exactly what speciation is. The question is, in the previous model that is very simple, can we modify it in a way that we see speciation? So in the previous one, there is no speciation. There is one type that is always getting better, but you always see one type. Or most of the time, you see only one type. And here we would like to see more than one type appearing in the long term. So of course, one very artificial idea will be to do what Darwin saw. So to consider now two islands, or two populations evolving more or less independently. So here there could be migration between the two islands, but it should be weak enough so that they don't interfere too much. And that we see two types of mutations. One that makes you more adapted to one island, and the other type of mutation that makes you more adapted to the other island. And that should produce, if you put all the parameters in the right way, that should produce two type of individuals. Two individuals adapting in a different way to the conditions in the islands. But what we would like to do here is something different. So the question here is rather, can we produce a model, a simple model, where we see a speciation, but where individuals are all subject to the same type of conditions? And this is what I say here. So I don't want to put two populations that are subject to different environments. I want them all to see the same. So how can we modify this model and make things still work? So the first idea that came to mind is to say, well, let us imagine that that we have seasons. And to make things simple, let us think that we have only winter and summer. And that we will have two types of mutations. One mutation that makes us better in summer, and the other that makes us better in winter. Yeah. So here we need to specify what a season is. So we will need a parameter that tells us how many generations a year has. And we will need to know also the length of the summer and of the winter. But if we know the length of the year, we also know it suffices to know the length of the summer. And here we model the environment with a +1 if we are in summer and a -1 if it's winter. Yeah, so these two formulas is only saying, well, summer is a +1, winter is a -1. And now we said we have these two types of mutations, plus mutations and minus mutations. And we define the type of an individual as the number of plus mutations minus the number of minus mutations. So one individual can go from 0 to 1 if it gets a plus mutation, and then from 1 to 0 if it gets a minus mutation. So minus mutations are back mutations if we want. And the fitness we'll define as before. It will be 1 plus Sn to some power, and this power will be the type. But it will depend on the environment. So if we are in summer, this means Rn equal to 1, then we want to have as much, so the k as large as possible. So a larger k will make us more fit. And in winter, Rn is -1, and therefore a small k and even a negative k will make us better. Yeah, the more negative the k, the better we are in winter. The more larger the k, the better we are in summer. And then we proceed more or less as before. So we say, assume that we start the evolution at time 0 with all individuals having fitness 1. And if we have constructed our population until time n, then the new generation is constructed very similar as before. So individuals choose a parent from the previous generation according to the fitness. So nothing new. And now we said with probability 1 minus 2 mu n, the individual gets the type of the parent. With probability mu n, we get a +1. And with a probability mu n, we get a -1 in the type. So could this work? Maybe some of you already imagine what is going on here, but I make a picture to make it more evident. So here the blue will represent the summer generations, and the red the winter generations, and then we have again the summer. So at the beginning, everything works exactly as before. So we start with only zeros, and individuals choose the parent from the previous generation. We may see some minus mutations here, but they will be deleterious in summer. So with high probability, they will disappear in the population. And at some point, you will see a beneficial mutation, like the blue one here, that makes you better in summer. And if we are lucky, this mutation will fixate. And now type 1 will dominate the population, the population. And then we may have another one, and then eventually we will get type 2 dominating the population in summer. And then at some point, the summer stops. And we only have individuals of type 2, let's say. They are all the same, so there is no selection so far. But at some point, there may be a back mutation coming into the game. So here, then the blue becomes white again. And white is better than blue in winter. So now then the white individuals have now a chance to fixate in the population. They have more chances to fixate. And then we may maybe even go to -1. And then at some point, the winter will stop. And then the summer start again. And now the whites are better than the red, and so on. So we see this idea of adaptation once more. So we are getting better. But then the effect of winter is, in a sense, not only stopping us for getting better, it's getting us back to what was good before at the beginning of the game. So there will be some kind of oscillation, but we will not see two types of individual getting this more distant and more distant. So this is not producing speciation. It produces some kind of oscillation. Eventually, you will move to the right or to the left, depending on the length of the summer or the winter. But you will not see that the distance between two types goes to infinity. So no chance to see speciation in this model. So what saves the game is dormancy. And dormancy is the capacity of organisms to go to a dormant state, and in this way escape the selective pressures and therefore maintain viability until conditions became favorable again. So what do we have in mind? So, well, first, dormancy is something that one can observe in nature. So many mammals hibernate in the winter. Many plants produce seeds which germinate after a dormant period. So we have the Atacama Desert where we see this whenever there is a bit of rain, and then we see this beautiful garden in the desert. And dormancy is something also observed in bacteria that go to a dormant state, for example, when there is no nutrients available. So dormancy allows individuals to survive periods of unfavorable environmental conditions, and it has been mentioned in some works that dormancy may contribute to speciation. So here I mentioned two papers, one which is a bit more mathematical by Jochen Blatt, Tobias Pohl, and Raj Tobias and Maite Wilke-Berenguer from last year, where they say that dormancy could increase evolutionary branching. And there is this other paper, it's a bit older, where they say that dormancy may contribute to a high speciation rate among South American tomatoes. This was new to me. So we thought, okay, so maybe if we add dormancy in our model, we have a chance to see speciation. So what do we have in mind? We have in mind as a model similar to the previous one. So individuals will acquire mutations that are advantageous in summer and disadvantageous in winter, and the other way around. And we expect to see two waves of adaptation. We will expect to see that some individuals will repeatedly acquire mutations that favor them in summer and then became very, very well adapted to summer, and others will get repeatedly, very regularly beneficial mutations that will favor them in winter and therefore get very well adapted to the winter. And we expect that the effect of the dormancy is that individuals may survive the seasons where they are less fit by going dormant. And this is why we think that dormancy could lead to speciation. So we will make this clear now in the model. So as before, we will have a population of constant size, but we'll have two parts now. An active part, so individuals that are awake, and this will be of size n. And there will be a dormant part, also of constant size. I will denote it by Kn. And when you are in the dormant state, you don't reproduce, and so this is the bad thing. But the good thing is that you don't feel selection. And now at each generation, Cn individuals, Cn is a constant, will go dormant. They are chosen uniformly at random. And other Cn's will become active, also uniformly at random. So the active and the dormant populations, they also remain constant. It's always the same amount that goes dormant and the same amount that goes active. And the remaining individuals, the ones that didn't switch from dormant to active, they evolve as before. So they choose the parent from the previous generation, and they inherit the type with probability 1 minus 2 mu n, or they get a plus mutation with probability mu n, or a minus mutation with probability mu n. So here we will have, more parameters. We have the n, active size, Kn, the size of the seed bank. The Cn is the size that switches from one population to the other one. Sn is selection, and mu n is the probability of mutation. So we have some general assumptions on the parameters. The first one is that, once more, Sn is a constant, we have a strong selection. The second condition is telling us that winter and summer are comparable. So we are asking that Vn, the length of the summer, divided by the length of the year, converges to a constant, and this constant is 0, 1, and we denote it by beta. Then we will ask the length of the year to be more than log of n, and this is telling us simply that seasons are not too short, so that mutations have eventually time to fixate. Cn, the number of individuals that is switching from active to dormant, should be much smaller than n, and this is to avoid that the transitions active dormant are too fast. And the last condition is a technical condition. The last condition is that the mutation rate, it will be small. We want mutations to be rare, but they should be not super small. Yeah, so they should be bounded from below by a power, a negative power of n. Okay, so let us try to see what is going on in one generation. So, and more precisely, let us see what happened, at least intuitively, the first time we see, or what happened to the population when we see a beneficial mutation. So we assume that all individuals have type 0, so this is at the very beginning, and assume that one individual mutates to type 1. So it gets one mutation during the summer. So this is good for him. So in the next generation, we know that individuals are picking the parent from the previous population, from the previous generation, according to the fitness. And this means that they will choose the single individual with type 1 with this probability. So the single individual with type 1 has fitness 1 plus S. The n-1 individuals with fitness 1, and therefore this ratio here is the probability that we are choosing the one with type 1. And since and S is, we said, is constant, so this will be more or less like 1 plus S divided by n. And we do this n minus Cn times. And since Cn is very small in comparison to n, this will be more or less n. Yeah, so a first order approximation. So this means that the number of type 1 individuals in the next generation will be a binomial, or more or less a binomial with parameter n and 1 plus S divided by n, and this can be approximated by a Poisson random variable with parameter 1 plus S. And well, this is when we have only one individual that has a different fitness. But in fact, if the number of individuals with type 1 is small in comparison to the number of individuals of type 0, they will not feel the presence of the other. So one can approximate. So one can make this rigorous. One can say that for a short time, the number of one individuals will evolve more or less like a branching process with a offspring distribution which is Poissonian with parameter 1 plus S. So when there is one mutation that makes an individual better than all the others in the population before, what you see at the very beginning is something that evolves like a branching process with a Poisson distribution. And conditional on survival. So if this mutation is successful, we know this is well known. This fixation, this mutation will fixate in more or less an order of log of n generations. And conditional on extinction, there will be not sufficient time for type 1 individual to become dormant. So this is because Cn, the number of individuals that switch to the dormant state, is very small in comparison to n. So mutations that are not successful, they will not have an influence into the dormant part of the population. So that's the idea. So this is what happened when we see a new fetus type in the population. And the other thing we need to know is what happened when there is a change of season. So imagine that we're in the first part of in the first summer. So we start with type 0 and we assume that type 1 appear in the population and start taking over in the full active population. And then the winter arrives. At that time, the dormant population will consist of type 0 and type 1 individuals. So type 0 individuals are the ones that were dormant from the very beginning, so from early in the previous summer. And there will be also type 1 individuals which become dormant late in the summer when type 1 started to dominate the seed bank. And then in the winter, well, we have type 1, but type 1 is not especially good in winter. And as we saw in the previous picture, some of the type 0 individuals that are in the dormant state may wake up and go active, and then they are super good. They are better than 1. So they are the fittest one in the active population now. And they will quickly take over the population after log n generations. And they will usually have enough time because UN is much larger than log of n. And then eventually there will be a new mutation that makes you better in the winter, and then you see type -1, and then type -1 will start spreading in the active population, and when it will dominate the active population, it will start populating the seed bank. And this idea will go on for the next generation. So let me now explain you this with a picture. So what is above the line, the red blue line, is the active population, and what we have below is the dormant population. The black lines depict the ancestral relations, and the orange lines, they are telling me which individuals wake up and which individuals go dormant. Yeah, so in this case, Cn is 2. So 2 individuals wake up and 2 go dormant, and and everyone is type 0 at the beginning. Then, as before, we see a mutation in the active population that makes you better in summer, and let's say this mutation is successful, so it makes us to dominate the population. And when we start dominating the active population, then most of the individuals that go dormant will be of the blue type. So the blue type will start dominating in the seed bank. And then we see type 2 appearing, so this darker blue start dominating the population, and then, well, winter starts. They are not especially good for the winter, but they are alone, so they don't have competition. And here we may have back mutations, for example, but back mutation will only take us to the previous blue color, so to type 2 to type 1 in this case. But something better can happen, and it's what we said before. Maybe we have a bit reserve of the type 0 individuals in the seed bank, and by chance, one of those wakes up and is super good, and it starts taking over in the population. So now it's the white one that takes over in the population, and then we see the -1 appearing, and so on. Yeah, so what we see here in the part above evolves very similarly to what we had before. But the seed bank and the miracle of the seed bank here is that when the winter starts, I don't need to go back the whole way to the white, because the seed bank may have enough reserve of those guys, those that were winning at the beginning of the previous season. And in this way, we can make big jumps in the type. So we can go, in this case, from 2 to 0. Okay, so this is the idea, and now we will say in which parameter regimes this works and how it works. So the first thing we need is to decide in which time scale we want to look at the model. So for this, it will be important to define the constant HS as the probability of survival for a branching process with Poisson 1 plus S offspring distribution. Why this is important and why this appears is because, as we said before, when there is a new mutation that makes appear that creates a fitter individual in the population, at the very beginning, the number of those good individuals will evolve as a branching process with Poissonian offspring distribution with exactly this parameter. So this H of S is basically, when I multiply it by the probability of seeing a mutation, is basically the probability of seeing a successful mutation in the model. So there are basically 3 natural time scales. One is the length of the year, of course, why not? The second one is rho n minus 1. Rho n, we said, is the probability of a successful mutation in the model. And rho n minus 1 is therefore more or less the expected number of generations until we see a successful mutation. So how much time we need to wait until we see a mutation that will produce one of these selective sweeps. And the third natural time scale is Kn over Cn, which is more or less the number of generations needed for the dominant type in the active population to start taking over in the dormant population. Yeah, so when we saw this blue type dominating in the active, I need this blue to dominate at some point also the dormant population. And this Kn over say n is telling me how much time I need so that I see the blue type or the new good type getting into the seed bank. So we will scale time with this rho n minus 1. Yeah, so with we will scale in the time scale where we see these selective sweeps appearing in the natural way. And we will distinguish between 2 possible regimes. One, where in fact all these 3 things happens in the same time scale. So, and by this I mean that Cn over Kn times rho n minus 1 converge to a constant that I will denote by alpha. And I will also ask that the length of the year is on the same order of magnitude as rho n minus 1. So this is one interesting parameter regime. And the second one is when seasons change before the active population populates the seed bank. So this is the first condition. And the second condition is telling us that the dormant population will equilibrate before a new mutation appears. And then there is a technical condition that tells us that dormant individuals will rejoin the active population sufficiently fast. Okay, so just a little bit of notation to state the results. xkn m will be the proportion of type K active individuals at time m, and ykn m is the proportion of type K dormant individuals. So here there is a mistake. This should be dormant. And skn of A is a threshold, will be the first time I see type K in the active population in a proportion that is larger than A. Yeah, so I want to see enough of them. And then I define dn of m as, well, in a sense, is the fittest type I have seen above the threshold A in summer, or if M is in winter, is one more. Is always the fittest individual in the given generation that has been present in a proportion larger than A. So it's the dominant type at generation M. So the first thing we want to say is what happened with this skn of A. So the first time type K goes above a label A. For this, we define RT. RT is basically in regime 1 the limiting environment. So it will be also 1 and minus 1. And it's defined in a way that is exactly the limiting environment that we defined before, the Rn. And now we consider two Poisson processes, inhomogeneous Poisson processes. In regime 1, the clock will move for the first one only in summer, and for the other one only in winter. And regime 2, seasons are changing too fast in the time scale, so we don't have a limiting environment. But a proportion beta of the time we will be in summer, and a proportion 1 minus beta we will be in winter. So this is according to the conditions we had before. So what we can prove is that, in fact, these times that I need to type K to be above the threshold A, after time scaling, these things will converge to these Poisson processes. So, and in fact, this is independent of A. So as soon as a type is above a threshold A, then this type will fixate. Okay, and well, these two theorems, they tell basically the same thing. They are just written in a slightly different way. So one is convergence in probability. So there is a coupling that allows us to do this. And it's telling me that most of the time, there will be only one type dominating the active population. Yeah. So here we are comparing xkn at generation M with an indicator. The indicator that at time M, K is the dominant type, as we defined it before. And this is telling us that most of the time xkn will be 1 or 0. So there is always, or most of the time, only one type dominating in the one type in the active population. And once this is proved, it's very nice, because now we know most of the time the picture in the active population is boring. There is only one type. So this means that if type K, say, is dominating in the active population, and the fraction of type K in the dominant population is Y, then in the next generation, what will happen is that I will get Cn, and I will lose a fraction Cny. So among those of type K, a fraction Cn may become active. So this is the way the proportion of type K dominant individuals will evolve in the population. So you see that this will become, in the limit, an ordinary differential equation, a very simple one. Well, this is when K is the dominant one in the good generation. And of course, if there is another type that is dominating, then instead of getting Cn all the time, we will lose all the time. So then there will be not 1 minus y, but there will be a y. So, so to formalize this, we define these functions f, k, and t. So they will be 1. So for K positive, will be 1 if type K is the dominant one and K plus 1 has not appeared yet and we're in summer, or 0 otherwise. And for K negative, it's the other way around. Yeah, it's only telling me if type K is dominating and the weather is good, then it's 1 and it's 0 otherwise. Then in regime 1, the proportion of type K individuals in the Dormant population will converge to the solution of this ODE. And the ODE is something like this. Yeah. So at the beginning you are 0, you have nothing of type K in the seed bank, and at some point type K start dominating in the active population, and if you are in the good season, then you grow exponentially until you go to the next season, to the where you are bad, you start losing exponentially, and then again back, and so on. And here, what is going on, why we didn't get until the top, is because now type K is not the better one in summer in the active population. Here, K plus 1 appears. So this is what we see in this other picture. So the K plus 1 was 0 until here, and here K plus 1 appears, and therefore the type K starts disappearing in the population. So this is what happened in regime 1, where all the scales work very well. In regime 2 is a bit more complicated because we have this fast switching between seasons. So what is going to happen is that, well, there will be some small intervals of time where something very strange happens. We cannot say what is going on, but out of that, what you will see is the equilibrium of this ordinary differential equation. So in a sense, you are going very fast here. So this is what is written here. So there is no limiting environment, but what you see is that YKN, when K is positive, will be beta. If you are if K is the dominating type in the active population, and it will be 1 minus beta in winter if K is dominating in the active population, and well, this is times 0. It's a combination of the two. And then you have once more this convergence in probability to this deterministic function. Well, almost deterministic by pieces, but you need to remove some delta intervals around the discontinuities of this function, so around the selective sweep times. And at those times, you cannot say what is going on, but very quickly you are either at beta or at 1 minus beta. And this ends the picture of what is going on. So we indeed see these two ways of adaptation in the active population and the seed bank acting as a battery that brings back individuals that were good in the previous season. So if you are interested, so this is the link to the archive version of the paper that is still under revision. And yeah, thank you very much.
Thank you very much, Fernando. So, are there any questions in the public? If no, I have some. I can start to give time to the others. There is a little, let's say, jump between the pictures and the results. So I feel like I need maybe some extra comment. But in particular, how do you see the speciation? Because I didn't catch it from here. Could you go back to there, please?
Yes.
Thank you.
So I think here the picture is the best thing because, in a sense, if you remember the very first picture where we have individuals that are getting higher types, so from 1 to 2 to 3 to 4 and so on. So what you see here, and if you forget the Dormant part, so we put a black box here, we don't know what is going on there, and you remove what is happening in the red part, there what you see is basically up to some noise coming from um, some for small proportion of individuals that are not fit. What you see is basically the same picture. So you see in the blue part, if you only look to the blue part, you will see type 0 is dominating, then type 1 is dominating, then type 2, then type 3, then type 4, then type 5, and so on. And if you go to the red part and you forget about the blue part, what you see is, well, type 0 dominates, and then it's -1, and then -2, and then -3, and then -4. So in winter, you see individuals that are very well adapted to the winter, winning all the time. And in summer, you see coming from the dormant state, you see coming the individuals that are super well adapted to the summer. So this is the way speciation appears.
Okay, it's not like they are simultaneously appearing both individuals, but like
No,
temporary separated.
no, exactly on the opposite. There is always only one that is dominating, and the other one is dormant.
Perfect, perfect. Now it's very clear.
Mhm.
I have another question, which are more like details on the model, but if I understood well, in the seed bank, the selection to go from dormant to active is uniform.
It's uniform, yes.
Is there any change if you, instead of doing uniform, do a selection also? You put the fitness like making more probable to get selected if you're more fit to the season, you know? It's like...
Yes, I guess this will change a bit the model. So there are some models um, where this activation is responsive to the environment.
Exactly.
And I guess this may be more adapted to some populations than this one, and this is maybe more adapted to other things. So this is really by chance. Here, as you said, there is no selection in the seed bank, but you may have models, and there are models where they consider this idea that individuals wake up as a reaction to the environment.
Okay. And also, a small detail, at some point, the mutation up to the, let's say, to the right and the left, are both with the same probability or with the same rate.
Mhm.
I imagine that if you put different rates, you generate a kind of a drift in the model.
Yeah, so exactly. So you don't need to choose mu n for. So we did it in the very symmetric thing because the results are a bit nicer, but that's not problematic as soon as they are of the same order.
Okay, okay, understand. Okay. Well, thank you, Fernando. This was very, very interesting. I'm sure we will keep discussing in another opportunity. Maybe
Very good.
for you.
So I have another question,
Mhm.
maybe. So somehow in your model, summer lasts for many generations, but for like Westeros, but like for our lifetime, can one make a sense of some the seasons lasting less than the reproduction time of the species?
So you want the seasons to be shorter than the reproduction time.
Yes. So
Uh,
somehow it is a weird type of questions in the sense that
so
it is
very,
hard,
very,
but it feels like realistic.
yeah, so you really want reproduction to be very slow. Um, yeah, so I think um, this will change definitely the model because here what we want, so one typical characteristic in this type of models is that you have the time to see these sweeps, no? To see when there is a mutation that is good and it's not washed out, then the mutation will fixate in the population. And for this, you need to have at least or the order of log of n generations Otherwise, you will see clonal interference. So you will see mutations. So you will see one winning, and then there will be another one that will appear, and the picture will be a bit more messy.
I see. So in a way, this is a good just to understand, it's a good representation of bacteria.
Could be, yeah, exactly.
I see. Thank you.
Are there any more questions? If not, we can thanks Fernando for his talk. No,
Thanks for the invitation.
I will stop the record now so we can get very